I'd like to thank the organizers for this opportunity to be here. It's great to be a part of this community where there's so much exciting physics going on. I'm not sure if I can really continue the excitement. Pierre and Mark, a hard act to follow, but I'll tell you a bit about the experiments we've been doing in Durham. So our emphasis has been on sort of nonlinear optics with Rydberg ensembles. So we're a bit more interested in the back action on the light field. So not so much on what the Rydberg atoms are doing, but more what the light is doing as it propagates through this Rydberg ensemble. But of course, in order to understand what happens to the light, we have to understand what's happening to the Rydberg atoms. So the first experiments that we did where we pointed out that there's interesting nonlinear optical effects using Rydberg ensembles were in thermal vapor cells, and we demonstrated this giant DC Kerr effect that you can get. And it's based on the idea of these dark states, which are superpositions between the ground state and a Rydberg state. And then you can exploit the nice properties that we heard about from Mark and Pierre of these Rydberg states in order to get these large optical nonlinearities. So this was reported about a year ago. And we continued to work on these dark states in thermal vapors, and in particular we're interested in experiments on electrometry. We can now tell a lot about what's going on inside our medium from just fitting these dark state resonances. So this just shows an example here where by looking at the shape of the resonance we can actually tell a lot about what the electric field is. So we can perform electrometry in situ in real time, and this just shows from these measurements we can tell what kind of charges are around inside our vapor cell and make quite sensitive measurements of electric field and try to understand also atom surface interaction or laser surface interactions and Rydberg surface interactions. We heard very nicely from Tillman yesterday about how these dark resonance signals tell you a lot about interactions between Rydbergs and surfaces, and I think we'll hear some more from Ben tomorrow on using these dark state resonances to probe the Rydberg atom surface interaction. So just to keep ahead of well, not really ahead, but to try and keep in the tail of Tillman, we're now going to nanocells just to keep up with him. So our collaborators in Armenia have just made a 70 nanometer cell for us, and we're going to try and look, well, initially for any kind of signal in that, but eventually it might be quite interesting to try and move up the ladder and get into this regime where the Rydberg atom is a significant fraction of the size of the vapor that you're looking at in these very confined geometries. So it's an interesting area, certainly in these very small confined geometries, to look at Rydberg interactions. Now, Tillman also mentioned that if you're going to look in thermal vapors and you're going to do something coherent, you have to go very fast. And so we've been trying to develop the tools to go faster. So we've been working with 1 nanosecond pulses, and not with Rydbergs yet, but our first experiments on probing the main resonance in rubidium on a gigahertz timescale, where we use the Faraday effect to do an optical switching of a 1 nanosecond pulse. And that's been reported together with my colleagues Paul Siddons and Ivan Hughes recently in this Nature Photonics paper. So we're starting to develop the tools where we can make this fast probing, and we'll try to extend this to Rydberg states in the future. So that sort of ties up a lot of our thermal vapor work, and I'm not going to really talk about that much today. So if you want to ask me any questions about this, I'm happy to talk about it in more detail. But I'd like to focus on one topic in particular. So this session was called Rydberg-Rydberg Interactions, so I need to say something about interacting Rydberg atoms. And I'd like to talk in particular about what happens when interactions start to appear between these dark states. So how is the dark state modified when we add in Rydberg interactions, and what type of nonlinear optical effect will that give us, and is it a useful thing? So this is the experiment, and these experiments are done on cold atoms as opposed to the thermal atoms, where it's easier to have a cleaner environment and see these interaction effects. I just mentioned we have one other experiment that's still in construction where we're working on optical lattices, and we're interested in the kind of schemes that Hans-Peter was talking about yesterday, a sort of controlled transfer where we couple via a Rydberg state to control the transfer between, say, hyperfine states. If you're interested in that, Ulrich Krohn is working on that experiment, and he's here, so you have a chance to ask him more details about this. So I'd like to focus on these Rydberg interactions in dark states. So there's a sort of fundamental question that we can talk about, which is sort of how does light interact with an ensemble of interacting dipoles? And why is that an interesting thing? Well, if you're in the nonlinear optics community, you're very interested in having a large nonlinearity. And if you have an interacting system, then this can give rise to much larger nonlinearities, and it also can give rise to higher order nonlinearities. So typically the first equation in, say, Bob Boyd's book on nonlinear optics is this one, where you basically expand your polarizability of or polarization of your medium in terms of powers of the electric field. And for atoms, because they got an inversion symmetry, you only get these odd powers. So you get a linear optical effect, and then you get a cubic term, which is the Kerr effect. And in principle, you can get a quintic term, but this is something very rare, and there aren't many quintic nonlinearities. So as you imagine, this power series is dropping off very quickly with these higher powers. But it's certainly possible in interacting systems that you can get sort of these higher order terms, and they also get these cooperative nonlinearities, where the whole medium is essentially cooperatively creating this nonlinear effect. So certainly dipolar systems are very interesting from that, because we have strong interactions between the dipoles. So if I take something like a dipole ensemble, so if I just take some permanent dipoles and I shine some light on them, and I can modify the dipoles. So in the example I've shown here, this is an orientational effect. I'm just orientating all my dipoles, and I change the optical response of this medium in some way which may be interesting. So this would be light modifying the dipoles. And this is typically what happens in a liquid crystal device. And actually the largest Kerr nonlinearities that are known currently occur in liquid crystal type devices. And there's this very beautiful device known as the light valve, which is essentially this type of situation where you shine on light on this medium, all the dipoles reorientate, and you get this very large Kerr nonlinearity. And there's a nice paper on this from last year. Now the trouble with these type of effects is they're essentially slow, these orientational effects. It's almost mechanical, and so it's a slow response. So what you would like for these nonlinear optical effects is both large bandwidth and large effect. So this is a very large nonlinearity, but with very, very small bandwidth. So the interesting question is, can Rydberg atoms bring us both a large nonlinearity and larger bandwidth? And that would be something useful for nonlinear optics. So what is the situation that we have in the case of Rydberg atoms? Well, we start typically with a ground state ensemble. So this is a nonpolar ensemble. We shine on light. It's still not necessarily a polar, but we now create, say, Rydberg atoms, which don't have a permanent dipole moment if we're just going to low angular momentum states. But then these Rydberg atoms can start to interact by dipole interactions. So we have a situation where the light induces dipolar interactions, and then there's going to be some back action onto the light field where these interactions then modify the propagation of the light. And that's exactly the type of effect that we would like to see and then exploit in these nonlinear optical type of situations. So let me first talk a bit about how does light interact with a medium. Sorry if this is too sort of basic, but I think we sort of need these equations as we go through. So the optical response of our medium is characterized by the susceptibility. And if I just take a two-level atom, I get a linear susceptibility, which is proportional to the A coefficient, or the dipole matrix element squared, number of atoms, things like that. And then there's a term here which is a decay term, so a decoherence term, which is effectively the lifetime of the excited state, and a detuning term. Now this is normally a linear, so this is a linear optical response of our system. Now how does nonlinearity appear? Well, it appears if this detuning here becomes a function of the electric field or the laser intensity. So if we had something like a Stark shift that shifts our resonance, then we get a nonlinear optical response. And that's the main way that nonlinearities appear in the interaction between light and atoms. So the useful things of this susceptibility are its real and imaginary parts, and the real part gives us the refractive index or the dispersive resonance, and the imaginary part gives us the absorptive resonance. And I've just shown on here what happens if we make this delta a function of electric field. You see it shifts, and that gives rise to nonlinear optical effects. Now, so if we want to do this on Rydberg atoms, we could just say, well, let's just take a two-level model. Take rubidium, we start in our 5s ground state. Let's go straight to a Rydberg state. And if we want to do this in one step, we know that it's tricky because we need a laser in the UV. But that's not the only problem. So this would give us UV nonlinear optics, which is interesting. But the big problem here is this susceptibility is proportional to this A coefficient, or the matrix element squared. So the matrix element that comes in here is from 5s to NP, where n is the Rydberg state. And this is basically decreasing fairly rapidly with n. So we get a smaller and smaller susceptibility. And yet these states are decaying. They've got many decay channels. So this gamma here is not decreasing as rapidly as the matrix element. So because this is not a closed transition, we can't get an enormous susceptibility from this. So it's actually much nicer to use this two-photon scheme that everyone is using because the lasers are convenient, but also for nonlinear optics this is a much more useful scheme where we have a nice infrared laser that's very convenient, and now the susceptibility that we're measuring is the susceptibility on this 5s to 5p main resonance, and it's then proportional to the matrix element, this strong dipole matrix element from 5s to 5p. So we get a large susceptibility in this system. Now there's another useful feature of this that was realized by Steve Harris and people in the early 90s about how you can get large nonlinearities associated with these free level systems because of the phenomenon of electromagnetically induced transparency. So now rather than dealing with a absorptive resonance, we actually have a transmission resonance because we have a dark state when these two laser beams are exactly on resonance. So when we're exactly on resonance, most of the light is transmitted, but we have this very large resonant feature which gives us very high dispersion and hence large nonlinearities, because if there's now a shift in this resonance, we get a very large change in, say, refractive index or in absorption. So these dark states then give us even larger nonlinearities than just normal absorptive resonances. And if we look at the susceptibility equation, it's basically the same, but it's sort of turned upside down now, and so the refractive index is inverted, and now we get low absorption exactly on resonance. And another nice feature is we can actually control the width of this resonant feature, which can be a useful thing because if you want to do nonlinear optics, you want to actually match the bandwidth over which you have, say, high dispersion to the bandwidth of your photon. So you can actually tailor the bandwidth over which you have large nonlinear optical effects in this case. So you have extra degrees of freedom that you don't have in the two-level system. So overall, this three-level system, I think that's the message I want to put across, is very nice for nonlinear optical type of effects. And there's many examples where this has been used in other contexts. So a very interesting thing for us is like, what's the wave function of the dark state? And there's a strong overlap with Thomas Anfor's talk yesterday, where he talked about these dark state resonances, where he was upside down, and I'm still the right way up because I can't do things on my head. So he was up here and then went down, and we start in the ground state and then go up. But the dark state resonance we can write in terms of this mixing angle. So it's a superposition of the ground state and the Rydberg state, and the amount of Rydberg state we get basically goes as sine theta, where tan theta is the ratio of the Rabi frequencies, so the probe Rabi frequency divided by the coupling Rabi frequency. So if we're in a regime where we have a very weak probe laser, so the probe Rabi frequency is much less than the coupling Rabi frequency, then we get the amount of Rydberg state basically goes as probe Rabi frequency over coupling Rabi frequency squared. So we can control the amount of Rydberg character in this state just by controlling the probe Rabi frequency. So as we increase the probe Rabi frequency, you get more and more Rydberg atoms. And you see this thing is the basis of the Stirrup technique, where by changing this angle theta here, we can go from all the atoms in the ground state to all the atoms in the Rydberg state. And essentially, by the way we're doing our experiments, we sweep through the resonance, and we have a kind of Stirrup process that goes along in this direction and then back again as we essentially vary this angle. So if we look at, this is how our experiments work. We have a coupling laser that's fixed in most of our experiments at a fixed frequency exactly on resonance from an intermediate state, which is a 5p in rubidium, up to the Rydberg state. And then we have a probe laser that we scan through resonance. So there's a little animation of this thing scanning through resonance. So there it goes. And what we measure then is the transmission of light through our gas. So there's just 4 panels here that show this for different intensities of this probe Rabi frequency. So if I here's our dark resonance. So this is our main resonance here, the main absorption resonance. This is the transparency window. So this is electromagnetically induced transparency. And what's interesting is what is the Rydberg population as we scan through resonance. And that depends very sensitively on the ratio of these 2 Rabi frequencies. So how intense is our probe laser? So as we gradually increase that, you see we get more and more Rydberg population. You see even in this case we get fairly high Rydberg populations, like about 40%. And you can actually get up to 70% Rydberg population just by sweeping through the resonance. So we can actually create quite a lot of population in the Rydberg state. And consequently, in principle, we've got a large Rydberg population, so we should be able to get large interactions as we sweep through this resonance. And that's the effect that we'd like to look for. So the question is what type of effects might there be, and why is this interesting? So there's actually been a lot of theoretical proposals where they've considered exactly this system of where we have these dark states involving a Rydberg state, And then you use this for some kind of quantum information system. So the first theoretical proposal along these lines was from Friedler, a group involving Michael Fleischhauer and Gerson Karitsky. And they made a proposal where they said you could use this scheme to entangle photons. So the basic idea there was if I put in one photon, I can create one Rydberg. So it's a blockade type of mechanism again. I put in one photon, I can create one Rydberg atom. But if I try and put in two photons, I can't create two Rydberg atoms. So the refractive index essentially for two photons is going to be very different for one. And I can use that to realize a photonic phase gate sort of device. And so that was something that sort of interests us and something we'd like to try and achieve. And then there are other proposals that also use this kind of scheme. So in this Moller paper, which is Klaus Mollmer's group, they're talking about adiabatic passage in this type of system and how that could be used to realize sort of exotic entangled states such as the GHZ states and other states that are of interest to this quantum metrology type applications. And then the one we heard about yesterday from Hans Peter is this mesoscopic quantum gate scheme where you can transfer many, based on having one Rydberg atom, you can then control the transfer of n atoms between two hyperfine states. So I think this system is certainly of interest for these sort of quantum information protocols. And the question is, what kind of Rydberg physics appears in there when we try to do the experiments. So let's look at now what happens to this dark state that I wrote down earlier when we add in these interaction effects. So the dark state we had was basically a superposition of ground state and Rydberg state determined by these mixing angles here. Now if I now take two atoms and there's no interactions, then I'd just get this thing squared. So I would get 1, 1, 1 freeze, 3 1s, and 3 freeze. But now if I put in a large van der Waals shift or dipole-dipole interaction, I have a blockade effect. And I can no longer populate this free state. So my two-atom dark state looks something like this. And you see what's missing here is this free term is not appearing anymore. And this dark state was written down in this Klaus Mollmer paper just last year. So this free state is actually replaced by 2-2. So now what's happened is that the interactions between the Rydberg atoms have suppressed the excitation of the doubly excited Rydberg state, and they've replaced it by population in this intermediate state. So normally in the dark state, this intermediate state is not appearing, but now due to interactions, it's appearing. And that's kind of a bad, well, you could regard this as a bad thing because we know this state is decaying very rapidly at 6 megahertz. So this would give a sort of broadening or suppression of this dark state resonance. So this is just populating these various coefficients here. So if I don't have interactions, my Rydberg state population goes as sine squared theta, which is this blue curve here. And if I do have Rydberg interactions, then it goes as sine squared cos squared from this term here, which is this red curve. So you can see, essentially, this is the blockade effect appearing in the dark state. So you can see there's a suppression of the amount of Rydberg population that I have, but it's not sort of dramatic, so it's not over a range that we can probe in our experiments, there's a small suppression of the amount of Rydberg population that we get. And just to emphasize that, the sort of region that we will probe in our experiments are this kind of range of this mixing angle here. As we vary the intensity, the probability frequency, we basically go from sort of around 0.2 to 0.6. And what's interesting is that I've just drawn on here a straight line because we'll get lots of straight lines later. You can see that the Rydberg population is pretty much scaling almost linearly over this region that we can probe when we have the effect of blockade on the dark state. So there's a kind of linear change of the Rydberg population, whereas here it would be more quadratic. So this is the effect that we'd like to look for then experimentally. Now we can make a more complete model, and I think this is the same model that Thomas Amthor was talking about for simulating his experiments. So you can solve the optical block equations for all these levels, so that would be a 9x9 system, and then you just include the effect of the van der Waals interaction or dipole-dipole interaction in this Rydberg-Rydberg state up here as a shift V dipole-dipole in the matrix. And then you can solve that and predict useful things like the transmission through your medium or the refractive index. And this is the sort of typical answer that you get out of this, what we call the pair model. So now if I just measure the transmission, so if I have no interactions, this is this thin black curve here. So I see a nice EIT transparency window. This is taken in the case where I have very low decoherence, so I can get 100% transparency on resonance. And then when we add in the dipole-dipole interaction, say for two atoms separated by 5 microns, I see a suppression of this EIT transparency down to a fairly low level here, and I also see a slight shift on the wings here, out in the wings. And I think this comes from sort of mixing in this intermediate state that you essentially modify this whole region of the transmission curve. Now it's interesting if you look at that also in refractive index. So this essentially comes from the absorptive or imaginary part of the susceptibility. But if I look at the real part, I get the refractive index of my medium. And essentially you see the same kind of effect. So with no interactions, I see a very strong dispersive feature here associated with the EIT resonance. And then when I add interactions, this feature is suppressed. And so I see this big change in the refractive index of the medium due to my dipole-dipole interaction. So this is an interesting optical nonlinear effect that's induced by interactions between my particles. So we can say this is a cooperative optical nonlinearity, which is an interesting thing. So it's a change in the refractive index induced by the proximity of another atom. So just by the fact that I've got a surrounding medium around me, that my medium is changing. And normally the optical response to the medium is usually not cooperative. So you're not really dealing with atom-atom interactions. Every sort of entity or emitter is dealt with separately in the medium. So these cooperative effects are certainly interesting from the nonlinear optics point of view. So what we expect to see in our experiments then is a suppression of this EIT transparency due to these dipole-dipole interactions, a suppression of the EIT, not a shift. So when we first started thinking about what we expected to see, we thought we might see a shift because there's a shift due to the van der Waals interaction, but it doesn't shift. It modifies the dark state and gives rise to a suppression of the EIT, but you don't observe a shift essentially because you don't populate this RR state, which is the one that's shifting actually. So we just expect to see a suppression. So we had some nice results on this and we saw a suppression, but when we presented them, people weren't so impressed as we were, because they said, oh, well, it could be due to ions, which is the story we always have in the Rydberg community, that everything could be explained because it's due to ions or black body radiation or something else. So we had to work a bit harder to convince people that we're not seeing ions. So we made an ion model, and we have a whole series of ion models actually. So we basically model our optical block equations and then allow some of the atoms to become ions, some percentage, and then we look at how the EIT transparency changes when we induce some fraction of ions. So we don't detect ions directly, but essentially with this type of method you can indirectly know whether there are ions present in your system. And then we can make transitions to either D states or S states, so we can look at the different effects. So here you see what happens for a D state. So when I have no ions, I have a nice EIT transparency, and then when I start to create some ions, you see it's just suppressed, so it's the same effect as we want to see due to dipole-dipole interactions. And then eventually with 4% ions, you see this starts to split up. So the problem with D states is a D state splits into 3 mod MJ levels, and they're going off in different directions initially. So there's both levels shifting out to both red shifting and blue shifting at the same time, which essentially you can see the 3 peaks in this green one almost. So that's difficult for the case of the D states to separate this van der Waals suppression or the interaction suppression from an ion effect. But with S states, it's much cleaner and much nicer because the S state, there's only one MJ level, which always shifts to the red. So if you do an ion model for the S state, basically you always see a shift due to ions on the red side. So with 2%, we see a small shift, and then with 4%, we see a larger shift. And the shape of this curve is now this Holtzmark distribution that's well known from ions. And you see this is very different to the effect that we expect to see from the dipole-dipole interactions, which is purely a suppression and no shift. So we can distinguish between these two possibilities using the S states. So the punchline here is that for S states, I expect a suppression without a shift, and this would be a good signature of dipole addressing of the dark state. So now I'll describe the experiment briefly. So this is our experimental setup. We just have a magneto-optical trap. These yellow beams are the laser cooling beams. And then we do all the probing along this axis here. So we have a weak 780 probe beam that's then detected on a fairly fast photodiode. And then we have a coupling laser that's counter-propagating. And this creates the dark states that we then probe and detect over here. And this is the experiment where you can't really see very much except the battery on the photodiode. And the experimental sequence then that we go through is we load our magneto-optical trap for a few seconds, then we cool down to about 20 microkelvin and densities of up to around a bit higher than 10 to the 10 actually now. Then we optically pump so that we can select a nice closed transition for this dark state resonance. And then we turn the coupling beam on first, and then finally we turn on the probe beam and then we scan it through resonance. And we actually scan it over a range of about 40 megahertz, and we scan it up through resonance and back down just so that 5 minutes, okay. So this is our resonance then. We scan up through resonance and then back down through resonance, and here's the EIT transparency. And this is very narrow actually, so for this data it's about 200 kilohertz. So this gives us a very high sensitivity to probe electric field effects or ionization effects or this van der Waals effect. And this was something we first did about last year in this paper here. Now, so as we increase the intensity then, we start to expect to see this van der Waals suppression, and here's some sort of raw data, so some single shot data showing this suppression effect. And this data is now on the 48S state, where we have a reasonably strong dipole-dipole or van der Waals shift. And so at very, very low probe powers at 5 nanowatts, we see a good EIT transparency, and then as we increase to 160 nanowatts, you see the transparency window is suppressed. And actually the shape of these curves exactly mirrors what this pair model is predicting. So that's fairly encouraging that we're seeing the effect that we expect. And then that single shot data that I said, there's some laser fluctuations on a shot-to-shot basis. So we actually average over many, many traces of this. And you see there's some broadening of the EIT transparency peak here. It doesn't go up to 0.4 anymore. It goes up to 0.3. But essentially the effect is the same. We see a suppression, but there's no shift in the data. And we've now investigated a number of different N states, 42, 48, and 59, and the behavior is consistent for all these S states. So what we're seeing here is a suppression of the EIT, no shift, which is characteristic of the dipole-dipole interaction. So let's just look at that in a bit more detail. Remember, the ion model we expect to shift, and whatever kind of ion model we construct, it's always a shift. So just to look, is there a shift? So we take all the data at different densities and plot them as a function of this probe electric field here. And there's some error bars because of the fluctuations of the laser frequency I mentioned, but there's really no characteristic shift in this data. So we can confidently say that we can distinguish between this dipole-dipole effect and the ion effect. But you would say, well, if you believe that there is an ion shift, then can you observe that? And we actually had to try quite hard to see a shift due to ions, to actually create some ions. Because our probe laser is so weak, it doesn't create many ions in the system, and there's not that many Rydberg populations. But what we do to see an ion shift is we scan on the blue side of the resonance, which is this pair potential. We scan up and down through this blue side twice before we make the probe measurement. And if we do that, we can actually see a shift. So here's the data showing an ionization-induced shift. And you can see there's quite a big difference here. It starts off the same with a nice transparency window, but rather than a suppression, we see that there's now a shift and a very large asymmetry on the red side, which you'd expect for this ion effect. And if we analyze all the data from this case, we see there's clearly a red shift in the data. So this data, we think, clearly shows the evidence of ions, whereas this data is clearly suppression due to the dipole-dipole interactions, which is on the dark state. And then the next thing we do is to extract a susceptibility from this data. And this just shows the raw data. And what we're interested in is the imaginary part of the susceptibility, which we get from the height of the transparency window here. And then we want to measure that as a function of our probe electric field. And what you see is it varies sort of linearly. So this is our nonlinear optical effect now, and it looks like a linear response as a function of the electric field that we're applying, which is a very strange thing because that would imply a chi-2 nonlinearity, which is not allowed for atoms. But it's not really a chi-2 nonlinearity. So if we turn back to our pair model, you see that actually what we expect is fairly linear. So remember at the beginning, this sine squared cos squared, if we look at it over a short range, it looks very linear, but it's just part of a nonlinear curve that's basically going up and turning over. So it's not completely unexpected that we see this linear response in the susceptibility. Now I just quickly want to mention what happens with the D states, because the D states are very different. Firstly, as I said, it's harder to distinguish now between the ion effect and this dipole-dipole introduced interactions. They've also got much stronger interactions. So if we crank up both the principal quantum number and go to the D states, we now have very large dipole-dipole interactions, and we can move into this resonant dipole-dipole regime where we start to get a 1 over r cubed interaction as opposed to the van der Waals interaction. And it's quite interesting what happens in this case. Again, we see a strong suppression of the peak. So as we go from 5 nanowatts to 25 nanowatts probe power, you see a suppression of this EIT window. I got to mention here that this could be consistent with ions, but this is hard to separate the two effects. But what's interesting is the nonlinearity that we observe in this case. So for the S states, we saw this linear change in the susceptibility. But as we turn up the density and go more into this resonant dipole-dipole case, we see a very strong higher order nonlinear optical effect. And in fact, when you go to the highest density here, it fits extremely well to a quintic nonlinearity. So this red curve is actually going up as a e to the 4th power. So it's a quintic nonlinearity. And just quickly, I'm rushing a bit now because I know I'm running out of time. But if we just take out the density dependence here and plot this as a function of our density, then we see that it's still going linear in density. And because I've normalized by density, that means that my susceptibility is going as density squared. So this is a cooperative effect. It's a two-body effect, so I see a cooperative nonlinearity. Now, as I've said, we don't know whether this is due to ions or dipole-dipole interactions, so we have to distinguish that. It could be an interesting optical nonlinearity, even if it's induced by an electric field or ions. But what we'd like to do now is do this on single photons and measure the phase and see if this is a coherent process and a coherent optical effect. And in principle, this nonlinearity is so large that if we focus to lambda, we have a large nonlinearity at the single photon level. So that's really the next step of our experiment, is to try and now focus our beams into a single blockade sphere so that the size of our sample is an optically dipole trap sample that's just within one blockade sphere. And in this limit, we should have this large nonlinear optical effect occurring at a single photon level. And as Tillman mentioned, essentially we're looking at light interactions with a single superatom or artificial atom, as Tillman called them yesterday. So we're just at the point now of this is our new setup with aspheric lenses, and we have electrodes to control the electric field in this case. And this little insert here goes inside our vacuum chamber, and we can get a 1 micron focus. And just to finally finish up, I'll sort of mention that we haven't forgotten about thermal atoms. And essentially, we use exactly the same setup with these aspheric lenses on these thin cells that have got a 5 micron interaction region to do sort of similar experiments, but in this fast time response regime. So I'll just summarize. So I hope to convince you that these dark states are an interesting thing, particularly in this sort of nonlinear optical context where we're interested in the back action of the Rydberg interactions on the light propagating through the sample. And I now think we've demonstrated that we can get a dipole dressing of the dark state, and this leads to a suppression of the transparency window. And I'd just like to acknowledge the people that have done this work, in particular John Pritchard, who's made all the measurements that I've presented. Alex is a postdoc on the experiment, and Kevin Weverall was a previous PRA that built the experiment, and Matt Jones is also collaborating, and we're supported by the Engineering and Physical Research Council. So thank you there.
I'm not sure I understood what, when you blue detune, why does that make ions?
So the idea is to try and excite pairs. So there's some experiments I think Matthias did when he was exciting pairs on the S states. And because of the way the collisions can occur, they can then transfer to attractive potentials and still create ions even though it's S states and you have repulsive interactions.
Okay, I'm hopelessly confused. Any other questions? We have time. Oh, yeah, tell me.
So this model is based on a two-atom picture, basically.
Which model?
You called it even a two-atom model, right? I mean,
yeah, it's two atoms.
The cooperative effects are two-body effects, basically, at the moment, right?
Yeah, well, not necessarily on this D state measurement. So you could take, if you take a van der Waals interaction, then you say it's an ensemble of pairs. But the trouble is, you need to know your pair distribution function. And the pair distribution function is determined by blockade effects. So like we were talking about yesterday, you've got some cutoff where you can't create a pair that's closer than a certain distance because of the blockade. So it's still a many-body effect because you've got to know the many-body physics in order to calculate the pair distribution function that then goes back into determining the optical response. So I don't think it's really just a two-body physics. If you've got more than two atoms within a Blockade sphere, then it's already a many-body effect.
So in your calculation, you have to assume some kind of pair correlation function, right?
We don't actually. So we just take the pair model, and then that. So we haven't tried to make a complete sort of quantitative model of our experiment. And what we do is we just make a qualitative comparison between our data and the pair model. But the pair model isn't the whole story of the experiment because we have an ensemble of pairs, and the pair distribution function is determined by Blockade effects.
You assume you have two atoms and some kind of fixed distance.
Yep.
Okay.
Yeah. But we don't do an ensemble average for that whole system, and that's difficult. So that's what Thomas was talking yesterday, is you need a better theory, and I think Thomas Pohl is maybe working on trying to do a theory that includes these kind of processes.
Yeah.
When you're modelling the effects of ions, are you assuming a sort of continuum, or are you
So we did
specific distributions and then averaging it?
We did different ion models. So we had one where the ions are just always there, and we had another ion model where they're created as we go through the resonance. And it doesn't matter what ion model we take for S states, they always give you a redshift. They give you different line shapes, but they always give you a redshifted line. So the one I've shown there is just the one where the ions are always there, but others give funny line shapes that sort of are very asymmetric. But whatever ion model you construct, it's always a redshift.
Actually, I also wondered, so in principle, this ionization mechanism also provides a nonlinearity,
Yeah.
right? So I'm just kind of wondering, in terms of the scale of this nonlinearity, can this really be comparable to, let's say, this kind of Rydberg-Rydberg interaction?
I think it can, yeah, because if you work out like an ion blockade radius, it's extremely large. So it's like 20, well, for our parameters, the ion blockade is like 20 microns.
It is actually larger.
Is larger, yeah,
than
than
the Rydberg blockade.
Yeah, yeah. So I mean, it could be, I mean, one thing we thought about turning that on its head and using it as a mechanism to detect single ions, for example.
Or use it for nonlinearity. It's a
Yeah.
in principle, it's a good, right?
Yeah, well, I wasn't sure whether it's a coherent because the ionization process is like a decoherent process, so maybe the coherence is not preserved of the.
Similarly coherent as a Rydberg blockade.
Is it? Yeah.
Okay,
Or
we
you
should
can turn it.
Yeah. Okay.
we should thank Charles again.